This is Crypto for Pen Testers by Thomas Tacek and Mike Tracy.
I do. I do too? Yep. Things are good? Everything's good? All right. Hi everyone. I haven't slept, so this is going to be awesome. Thanks for coming. We're just going to get started. So one thing before we get into this, while Mike gets this set up. So this is kind of long and it gets dense. So we're going to do questions. The talk's broken into sections. So
the talk's actually broken into rounds. So after each round, we're going to have a Q&A. So we're just going to stop after each round. And if anybody has any questions, feel free to raise your hand and ask it.
So questions at the end of each round. Valid questions get a sticker. So it's an awesome sticker. Ask questions. So anyways, I want to show you something cool here. So let's get into it.
Right. So we have a web application that allows us to download a report, right? So whenever we see something like this, when we're pen testing web applications, what's the first thing that we try to do with something like this? Well, we obviously see if we can try and download arbitrary files.
No developer in the history of web application development has gotten file download right the first time they implemented it.
Yep.
So the first thing we have to do here is see if we can download an arbitrary file. So let's look at the URL.
So we take a look at the URL, and there's a lot of things we could try to do with this, right? We tried null byte injection, we tried doubling the file name parameter, we tried ... we try all that stuff, and every time we do, it looks like the Mac is killing it. It looks like something is happening in the message where every time we do it, we get a signature verification error.
I'm sure there's some like awesome OWASP guide to testing file downloads and all that, but like you look at the URL at the top of the screen there, and the file name is in the URL. And that's blood in the water. It's a moral imperative that we be able to download the file when the extension and the name of the file is in the URL. So he's trying all these things, right? He's trying like doubling up the file name argument, moving the equal sign around and all that stuff, right? It's not working. So what's keeping us from being able to download the file? Well, this is crypto for pen testers. Obviously, it's this Mac thing at the end of the URL that's keeping us from doing that, right? And we look at that, right? We look at that Mac string, right? It's a 20 byte long, it's 40 bytes long, but it's hex encoded, right? It's a 20 byte long string, right?
So it could be a lot of things, but
in the real world, you see a 20 byte long hex string at the end of a URL. That's probably SHA-1.
Most likely.
Right? So you try the obvious thing when you see that in the URL, right? You take the SHA-1 of the file name itself, and you see if that's what it means. Because there's a developer out there that thinks that that's cryptographically strong because SHA-1's a cryptographic hash function, and the URL is authenticated, right? Seen it happen, clearly does happen. You try it, doesn't work here, right? So obviously something more is going on here than us just hashing the file name in the URL. There's some kind of secret that's probably mixed in with this hash that's keeping us from being able to compute the hash without knowing that secret. Only the server knows the secret. And that's the whole security model here, right? There's a secret key and this is called a MAC. It's called the message authentication code. And we think this is a MAC based on SHA-1 just by looking at the length of the string. So I want to show you a couple of things about SHA-1. Hopefully if I can give you just a couple of little facts about SHA-1, I can show you how to break a very, very common SHA-1 message authentication code. So at the top of the screen there, that's the hash from the URL from the previous slide. So there's two things I want to show you here about SHA-1. The first thing I want to show you here is this. So the line in the middle of the screen there is the same as the line on the top of the screen there. When you look at a SHA-1 hash, you're accustomed to looking at a big, long, random hex string, right? That's what SHA-1 hashes look like, right? In reality, SHA-1 hashes are not long hex strings. What they are really is a sequence of 5 32-bit integers. SHA-1 calls them registers, right? And by convention, when we're looking at SHA-1 hashes, we concatenate them together and we show them as a big long hex string. Kind of the same way we would do with an IP address. Like we do dotted quad notation for that data structure. Well, for this, instead of showing you the registers with a colon in the middle or whatever, right, we just cat them together and show you the big long random hex string. But very important to understand here, right? First of all, SHA-1 hashes are actually a sequence of 5 integers. Now the second thing I want to show you here is going to blow your mind, right? The second thing here, that string at the bottom, if you look in any SHA-1 implementation, just kind of glance over the code, what you'll see in the code is a place where it says, here are the SHA-1 magic numbers or the initial numbers or the initial register values. Now if you read a lot of crypto code, you see a lot of magic numbers like that. Right? And usually they have something to do with the Hamming, weight, distance, whatever mathy stuff. I'm terrible at math, right? And you don't pay much attention to them. But here, the magic numbers in SHA-1, very simple to understand. The magic numbers in SHA-1 are actually the hash of no data. It's actually the initial starting hash of SHA-1. It's the hash of epsilon. Every other SHA-1 hash is related to this SHA-1 hash by permuting it based on the data.
Which we're now going to call the hash.
So it's like the hash. It's the origin of all other SHA-1 hashes is this. So if you look in the SHA-1 implementation, you're going to find the hash from which all other SHA-1 hashes spring. So why am I telling you this? So what we're going to do here is we're going to show you an exploit based on the fact that all SHA-1 hashes are related to that original hash that we just showed you. And this exploit is going to allow us to add additional data to the end of that URL and still get a valid MAC for the URL, even though we don't know anything about how that was actually computed. And so being able to do that is going to allow us potentially to download arbitrary files because the application is coded to assume that we can't possibly generate a valid MAC because the MAC is protected by the secret that was hashed into, it. And hashes don't leak any information about the data that you put in there. And we're going to kind of disprove that a little bit. The attack that we're going to do here is called length extension. It's kind of an old ancient attack. And it's kind of tricky.
Yeah, but so if you go out and read a paper on this, right, it makes it look really hard, right? But the 5 things that you see on the screen are the things that you actually do to make a successful SHA-1 length extension attack one-by-one steps.
And
right?
if you can understand each one of these steps, I think you can put these steps together pretty straightforwardly and break certain classes of SHA-1 MACs. So the first step. So what you're looking at on the screen here is a pure Ruby. Ruby's our programming language. You can use whatever programming language, but this is a pure Ruby SHA-1 implementation. Yep. This is roughly what you would get if you went to Google and searched for pure Ruby SHA-1 implementation. And we're going to do a little bit of surgery on this right now. So the first thing we want to do, we introduced you a second ago to the concept of that hash, which is going to be embedded somewhere in that code there. Mike, what I want you to do is allow us to override the value of those.
Okay, done.
So that was easy. So Mike, I think what you did there was you added an argument.
So all I did was I added an argument to the function that allowed us to override setting the registers from the original hash register value. That's all I did.
Straightforward. Remember we did that. Next slide. So next thing, SHA-1 works on blocks of 64 bytes of data at a time. Now, real-world input almost never comes out to exactly 64-byte increments. So what SHA-1 does is it always pads the input to the hash. So before it actually runs the SHA-1 algorithm, it's going to take the input and it's going to pad it out. And what we want to do here is we want to disable that padding so that we can control it ourselves.
All done.
Okay.
So all I did here was take the fact that they're calling the pad function with the string that gets passed to compute hash, and I just say, don't do that. It's that simple.
Okay. So next part. This is a little bit more tricky. So when we saw the hash in the URL that we were looking at a second ago, we presume that that's the hash of some secret and the URL itself, and that's what actually hit the SHA-1 function.
Yeah, we can't
But that's not actually what hit the SHA-1 function, right? What hit the SHA-1 function is some secret we don't know, and the data in the URL, and then the padding that rounds that back up to 64 bytes. And what we have to do is, even though we don't know the length of the secret, we have to make a guess about the length of the secret, and then compute its valid padding.
So in other words, we can't just add data to the URL, right? We need to create padding in order to extend padded arguments in order to be able to create new URLs. So in order to do that, we need to actually be able to compute the padding, right? So we write a little simple function called compute_pad that actually, so SHA-1 padding is literally appending byte 128 and then a whole bunch of nulls and then a 64-bit integer that is the string's length, right? So the way this attack works is so this message that you see on the screen, in order to do this, we have to guess the length of the secret, right? So in this case, we've guessed the length of the secret is 10 bytes. And now we've created a message that's that long, right? Minted with the fact that message is 64 bytes long.
And what we have there ostensibly is the padding that hit the SHA-1 function on the server when it hashed the URL with its secret. Now what we're going to do is we're going to take that data, it's going to be binary gibberish, and we're going to slap it on the end of the URL. We're going to call that glue padding. And the reason that's glue padding is it's going to enable us to put more data at the end of the URL and then compute a SHA-1 hash for it. So that's why we call it glue. It glues our data together. So next step here, so we have our own data that we want to add to the string, right? In this case, it's the string test, just because we're testing this out. We're writing a test case here, right? And what we're going to do is we're going to compute the padding for that now. Like the final message has to have padding too. And we have to compute that, and to get the hash for it, to make it a valid hash, the padding for it has to be right. So Mike, you're going to compute the padding.
But in this case, all right, so in order to create the hacked padding, right, we need to take the first set of data that we've now extended with glue padding and consider that to be 64 bytes. Then we add our new string test, and that's now 68 bytes. Now we make a new block that has this hacked padding on it, and the length at the end actually says 68.
So all we've really done here is we took the normal padding function, the normal padding feature of SHA-1, and changed it so that we can lie to it about the amount of data that we gave to it. So all we're doing is we're changing the length at the end of the padding. So now the next thing, we're going to put this all together. And what we're going to do is we're going to take our pure Ruby SHA-1 function, the core SHA-1 function. We're going to take the data that we want to add to the URL. In this case, it's a test case just to see if it works. But in reality, it would be like another file name, like another parameter. That would be another file equals whatever to see if we can download other files. We're going to take that data and its valid padding, potentially it's valid padding, and we're going to feed that to SHA-1. But when we do that, we're going to override the registers, the initial values for the SHA-1 function from like 4 slides before that first step. And we're going to make it, instead of the initial values for SHA-1, we're going to make it the values from the hash in the URL as our starting point instead. And we're going to get another hash that comes out of it. Now, that SHA-1 hash that we just created probably isn't going to work.
Yep, but that one's going to work, right? So basically, the way this attack works at the end is for some number of lengths of secret guesses, let's say 1 to 100, right? I'm going to mint new URLs that look exactly like this. And if you look at this URL, right, it is basically the original parameters with the padding that we tacked on, URL escaped, plus the new MAC that we minted, plus the new file name that we're trying to download, right? So this works a couple of ways, right? If it takes 2 file name parameters and takes the second one, we download a file. If it's canonicalizing the arguments and we pass something like f equals ILName report and tack on a new file name parameter, we download arbitrary files.
Either way, though, what's going to happen is that hash wasn't going to work the first time because it's not likely that we precisely guess the length of the secret the first try. So we have to guess, instead of cryptographically hard guessing of numbers of 2 to the 128th power, we're going to guess a number between 1 and 100 of the likely length of the secret. And each time we try that, we're going to send the server a string with a test case in it, maybe just test, and we're going to look at the errors that we get back. And when we get the one that has the right secret length, presuming the server is vulnerable to this very common flaw, we're probably going to get a different error back.
Right. So what happens is every time I send something that's not right, I get the signature verification error. When I send something that is right, I get a file not found error. We win, right? Because now we can just, instead of generating a file not found error, let's just look for files that are actually found and download them.
So that shouldn't happen. You have you send a variety of different attempts at the length of the secret to the server, and you get a different error message. The only reason we're getting a different error message is because we passed the MAC, right? The MAC is stopping us at every other attempt, but the one time we get the length right, it passes. Now, SHA-1 cryptographically strong, you have a better chance of being struck by lightning 5 times, standing where I am right now, than getting an input to SHA-1 that's going to accidentally pass the MAC function. So the minute we see a response from the server that has a different error, we know the server is vulnerable. The minute we know the server is vulnerable, we know how to mint our own hash for any given extension of that URL. And all we got to do is take that URL, slap the right padding in between the original URL and our content, and then compute the right MAC for it, and the server is going to be fooled. It's going to think that's a valid MAC. It is a valid MAC because of a property of SHA-1. It shouldn't be possible to do that. That should be impossible, right? Like, we're talking about a SHA-1 hash that includes a secret that we don't even know about. But because the developers that build things like this don't understand the way that SHA-1 actually works, lots and lots of things are vulnerable to attacks like this. As an example, a couple of years ago, the people that were vulnerable to something like this was Flickr. The entire Flickr API had a MAC that worked exactly this way. That was a finding from Tai Duong, who works with us. I don't know if he's in the audience, but it would have been nice if he was. And Juliano Rizzo, also both smarter than me. That was originally one of their findings, but this comes up a lot.
You can actually Google for code that has this flaw in it. There's actually one guy who wrote a Perl module for Apache that does SSO that has exactly this bug in it.
There's a simple fix for this problem, right? It's called HMAC, and what you do is, instead of hashing the key, instead of hashing a secret key and then the data, what you do is you hash twice. You hash hash once with the key, and then you hash once without the key in 2 different steps, and that blocks the attack. But you'll find code out there, and that's called HMAC, and you'll find code out there that says it's doing HMAC, but the developer thinks that HMAC means hash MAC. And now you guys know HMAC is an actual construction. It's specifically designed to hash the data twice to not have this flaw. So you can ask questions now, or we can introduce ourselves. I'm Tom. This is Mike.
Hi.
Did that make sense to anybody here? What we were just doing? Like, did anybody roughly follow it?
Is there anybody who didn't follow it at all? Because we want to talk to you after the talk's over.
So this attack is kind of old hat. You have friends that think this is really lame, right? Like, this is well-known, ancient, who cares, right? But your friends are not finding this on pen tests.
You also have kind of the people who look at who are on a web app pen test and they look at a great big random looking blob and they get scared and they say, oh, that's random, that's encrypted, that's got to be secure. I'm going to go find the next cross-site scripting bug.
I started Modisano like 5-6 years ago. I work with amazing testers. We follow up on engagements on apps from other firms with really amazing testers on them. We see what people find and what people don't find. People don't find stuff like this. I don't know, push comes to shove, I don't really know how many people, people say they know, okay, SHA-1 has length extension vulnerabilities. How many people really know how to exploit that? Or even really just write a test case for it to see that it's there. People can sometimes find this stuff if they're looking at source code and they know what to look for. But you show them a hash in a URL. Do they catch this? Well, judging from what you find in applications that have been tested 10 times before you, people don't find this stuff.
Hey Tom, the best box is a busy box. So what do you say? Let's keep moving.
Mike just cut me off. I don't even know what that means, but okay. Yeah, there you go. Go.
So we're going to give you a more. We're about to give you a more complicated example involving a cookie.
I had a whole speech.
This time it'll be a lot more clear what it is that we're looking at. So again, we have a web app where this time we're actually able to edit our profile, right? So all the information in the profile, it's a web form, you post the form, you get back, and your profile's changed, right? But this time, every time we post the form, we get back a set cookie response, a set cookie header in the response that's telling us to reset our profile cookie to some big, long, base64 encoded, yes, we know that it's base64 encoded string, right?
And when you log into the application or when you change your profile, that changes, or parts of it change.
Right. So it looks to us like this cookie, since this cookie changes every time we change our profile, it's holding part of our profile information, right? So when we see things like this, we take samples of them.
We have a whole step-by-step.
Oh, we do, actually. We base64 decode them. We take lots of samples. We test the entropy of those samples. We log in as multiple users.
So you're looking at a big, long, random binary string. This is a really super common web app pen testing conundrum is you see the big, long binary string and you assume it's encrypted somehow. You play with it. You change bytes. You change one character to A or something like that, and it doesn't work, and you move on because it's encrypted, right? And there's a couple of things that we do here to try and get a handle on what it is. We have no idea how that was, what that is, if it's compressed or encrypted or whatever, right? But there's a couple of different things we can do to get a handle on it, right? Obviously, like Mike said, the first thing that we want to do is decode the data. We have to be working with the raw bits of the data that we're looking at here to actually do anything with it. So first, we strip off the base64 encoding.
Yep. Then, so we strip off the base64 encoding and take a look. And then that look says we run it through ent. Everybody can download it with random.zip. We see that it's got high entropy.
Anybody here, by the way, have ent on their computer? How many people in this room, by the way, test web apps? You're in the web app track. Do you know why you're here? It's terrible.
They're here to see you, Tom.
I don't think so. Download, even if you don't test web apps, put ent on your machine. You feed data to ent, and it tells you the number of bits per byte of randomness. And you can look at that result. You collect a bunch of samples, cap them all together in a file, run ent on it. Ent will tell you how mathematically random the input there is. Now, in this case, we do that, and we run ent on it, and it says 7.5 bits per byte are random. It's very random. It's either going to be compressed or it's going to be encrypted at this point. Let's take a stab right now that it's encrypted.
Right, so then we're going to bit fuzz it, right?
You know how to bit fuzz things?
So I think I do. So all you do is, so we send this cookie in the request, and every time we send it, we change 1 to 3 bits randomly somewhere in the message to see if we can generate different kinds of errors. And the errors, the reason why we're doing bits instead of bytes is because we don't want the application logic to change. We actually want to get encryption errors, not application errors.
So take the cookie, 1,000 variants of the cookie, each one with 1 to 3 bit errors, right? And again, we're doing that so we catch crypto flaws or crypto errors and not application errors. We want to get an idea of what the crypto is doing. Now, we do that in this case, and we see something important right away, right? Which is that we get different errors. Not a lot of different errors, but a couple of different errors. At the end of this talk, we're going to show you how to see our sample code and play with this yourself. But different errors, right? And that tells us right away that there's no message authentication code on the message. That's not authenticated. It's encrypted maybe, but not authenticated, right? We know that, again, for the same reason we knew before, that struck by lightning 5 times, whatever, you're not going to accidentally pass the MAC function. So if anything, any error in that message gets a different error, then there's no MAC checking it. So we find out that there's no MAC here, right? So it's almost the first thing we do with any time we see a big, long, random message. Just do that, right? Take 1,000 samples, take 1,000 variants, bit fuzz them, see what the errors are. Sometimes you learn exactly what's going on just from that. In this case, we don't learn anything that's going to allow us to do anything awesome yet, except for the fact that the message is authenticated.
So the simplest thing to do is just to stuff 100 A's into it and count the number of blocks, right?
So counting the number of blocks, Mike, how would you do that?
So I would stuff 100 A's into it, and then I would take a look at the response and see how many blocks are actually generated by the return. And this is that message with 100 A's stuffed into it, aligned by blocks, right? So you can look at this and see this message is modulo 8 or modulo 16. It's either 8-byte blocks or 16-byte blocks.
And you know that because you're seeing 5 times in that message repeating ciphertext blocks. The ciphertext, we stuffed 100 A's in there, and we saw ciphertext blocks effectively collide with each other. This is very, very, very bad. What you're looking at here is ECB mode encryption. We're going to try not to call it ECB mode encryption for the rest of the talk. What we're going to call this is block cipher encryption in the default mode encryption. Default mode encryption is bad for a wide variety of reasons, not least of which is because you can cut and paste blocks around and all that. Because the blocks that are repeating are 16 bytes long, it's a 16-byte block cipher. It's probably AES at this point. But the awesome thing about this is we don't need to know what the block cipher is here to annihilate this. Right? The fact that it's encrypted in the default mode is enough for us to do terrible, terrible things. Not just shuffling blocks around. Instead, what Mike's going to do here is he's going to show us how to decrypt the whole thing.
So we're just going to straight up decrypt the message, right? And again, we're going to do something that looks kind of tricky, but we're going to break it down into really easy steps.
What are we doing? Oh, we're trying to get the prefix of the message.
Yeah. So
we have to count the number of bytes that occur prior. So think about the message for a second. We stuffed A's in the message changed, but not the whole message changed. Just a big chunk in the middle was where we saw the repeats, right? So there's some amount of data in the message that comes before us, and there's some amount of data in the message that we appear to control completely, and there's some amount of data in the message that follows us. And what we're going to decrypt is the stuff that follows us right now. And what we need to do in this step right here is find out how many bytes preceded the bytes that we control in the message. Steps.
Right, so these are the steps to actually do that, right? So the first thing we're going to do is we're going to stuff the user input 1 byte at a time, right? So we're going to start with A, then we're going to go to AA, then we're going to go to AAA.
Each time we're doing that, we're making a new request and seeing what comes back.
Right? So as we do that, right, then we're going to check each time to see if any blocks repeat. We're going to find the magic block, right? So if you remember back to the hex dump, we know that the encryption of all A's is that string. Right? So now we just do that. We just pad the user input with A's.
1 request at a time.
1 request at a time until we actually see that happen.
Until we see like the Rosetta Stone block. That's the block that repeats. It's the block that we know, because we're stuffing A's in there, is the encryption of 16 bytes of A's.
And then through the magic of subtraction, we actually figure out what the prefix length is, right? So basically, I put in A, I put in AAAA, I keep putting in things until, oh, what happened?
That would have worked a lot better if that hadn't happened.
I know. Sorry. Ooh, we found the magic block, right? So through the magic of subtraction, we put in that many A's. That padded something out to 32 bytes. We subtract that number of A's from that, and we come up with the number 18.
2 points here, right? 2 points to remember here. First of all, it's very straightforward in default mode encryption to find out how many bytes precede the bytes that you control in the message. And here, there's 18 bytes in front of the stuff that we control, and hold that thought.
So we need to know that so that we could actually decrypt the message Hollywood style.
Hollywood style. This is a term that I have stolen horribly and ruthlessly from Tai Duong and Juliana Rizzo, but like, I don't know, the shows that you watch.
Yeah, so like imagine Jack Bauer on 24, right? And he needs to get into a vault, right? So he gets this machine that he puts over the lock, and it starts rumbling through numbers until all of a sudden 1 number appears here, and then 1 number appears here, and then 1 number appears here, and then the counter's going down to 1 second, and all of a sudden the last byte comes on, and then he stabs somebody.
And encryption is not supposed to work that way. You guys all know, everyone here knows, encryption does not work that way. It does not work the way it looks on the screen. That's not how encryption works.
This does.
Here.
This does. It works exactly like that.
Except in the default mode of block cipher encryption, where it works exactly that way.
We are doing exactly that. Like if you see this actually happen, it looks exactly like that.
So the attack here is a little bit tricky, but again, just like with SHA-1 and just like when we found the prefix bytes, we're going to break into steps. If you can follow the steps, you can decrypt arbitrary messages encrypted with AES or Blowfish or 2Blowfish or whatever the hell it is. No problem, Hollywood style. So Mike?
So the first thing to do is to make a dictionary. So we know what our we know what our Rosetta Stone block is. It's all A's, and it decrypts to this, right? So now if we make a dictionary of blocks that are 15 A's and a B, 15 A's and a C, 15 A's and a D, all the way through all 255 ASCII codes.
We know what 16 A's look like because it repeats. When we see that repeat, we know 16 A's looks like this. What we want to know is, but we don't know what 15 A's and any other byte looks like. That's a fundamental property of AES. That's why AES is unbroken. So instead what we're going to do is we're going to try 15 A's and then every possible byte that could be there. 15 A's and a B and a C and a D and all that. He's going to build that dictionary. And he's asking every time to build that dictionary, he makes requests of the servers with his profile populated, with like his email address or his name, with 15 A's and a B, repeated a bunch of times. He finds the repeating block, and there it is. And now he knows how to encrypt that one block.
Right. So the next thing we do is set up a plain text alignment where we know that the prefix is 18 bytes. So we pad that out to be a complete block. So we add 14 bytes to that. We know we're trying to decrypt this much information, right, that comes after the plain text that we control, and then we add 15 bytes of A's. We add 15 A's to the end of the message and leave a byte blank. And that byte, when we send the request to the server and get the response back, that byte is actually the first byte of the stuff that comes after the message that we control.
So that condition, 15 A's and a B, 15 A's and a C or whatever, we want to induce that condition organically in the message. So it's 15 A's and the one byte we're looking for.
So simply stated, when we get the response back, we compare it to all of our dictionary entries, right? And all of a sudden, we know that next character is a pipe byte, right? And the decrypted byte is a pipe.
Through the magic of comparison, we have decrypted one byte
of
the message that we were looking at there. We now know that the next byte in the message is a pipe filter. And what does that mean? It means if we can do one byte, we can do all the bytes, Mike.
So again, you just keep doing that over and over again. And what you do is you align 15 bytes of known decrypted stuff, right? So it's either A's and known decrypted bytes, and then you just keep subtracting one from your stuffing.
So
and
all A's and a pipe and a D.
All A's and a pipe and an
A.
Right. And you just keep on backing the truck up, and all of a sudden you're decrypting the entire message.
I am going to judge how well this talk goes by how much water I can drink while I'm on stage.
You can probably drink a lot of water.
I bet I can.
I know.
Keep going, Mike.
All right. So this is the entire decryption, right? We decrypted that many bytes, and our stuffing size at the end was 19. We stuffed too much. I overshot. Big deal, right? But we look, and this is the contents of the cookie, right? So the payoff here is that if you look at this cookie, it's our profile information, and then all of the information about our account is tacked onto the end, including admin equals 0. Right? If there were some really trivial way for me to change admin equals 1 and send that cookie back, that would be a complete win. And since we can now decrypt the message, it's absolutely trivial for us to encrypt that message and send it back to the server.
Show of hands, how many people can see how easy it is to put admin equals 1 in the message instead of admin equals 0? A fair number if you can, right? This is default mode AES encryption, which means that each one of those blocks was encrypted independently of every other block. No state was saved in the message. That's bad, right? Like in well-encrypted data, the whole message is one big long random string where every bit in the message is mathematically uncorrelated to every other bit in the message, right? But here, because there's no state, it just runs AES a block at a time because it's the default mode. Every block is independent of every other block, which means we can shuffle them around, reorder them. We can put admin equals 1 in our username and get a block that has admin equals 1 in it, and then stick it in the message.
So that phone number is actually the phone number for the Secretary of State's office, specifically the DMV, and I'm mad at them. So if everybody after this talk would be so kind as to call that number, I thank you.
Okay, Mike. That was
How long did it take you to brute force your AES key?
Brute force our AES key. We don't even know that it's AES.
Yeah.
It is AES. When you looked at that animation back there, and Mike, don't put it on the screen because it takes forever. When you looked at the AES thing on the screen, that was actually, Mike actually went and used our magic and made little screenshots of his exploit running while it ran a frame at a time. So, but we did that without even knowing. I wrote the server side of that to do the demo for it, and it uses AES, but he doesn't even know that. Yeah, it could have been Blowfish encrypted. It could have been Rindale with a bigger block size encrypted, right? Yeah. You don't even have to know. There's no key involved.
Could be
you can decrypt the message completely without a key. And this is, again, this is AES in the default mode. If you're looking at generalist developers who are building web software that have been, for a reason I cannot fully understand, provided with the tools to encrypt data. If you're looking at software like that, 3 times, maybe 4 times out of 5, they're using the default mode AES encryption. There's a reason for that too, because when the mode that does not have this problem is called CBC mode. There's other modes that don't, but the most common mode is CBC mode. And to make CBC mode work, you need a whole other parameter to the encryption. It's called the IV.
Developers don't like parameters.
They especially don't like them when they're called. They don't like them when they're called initialization vector, which sounds really scary. It's a simple concept. You don't care about it right now, but it takes more work and it takes more reading to figure out how to do CBC mode encryption. But the default mode works just fine, and it produces data that sure looks encrypted. It's just trivial to decrypt. And so a bunch of the time when you're looking at software of any sort, if it's got encrypted blobs in it and you verify that it's encrypted, chances are you're going to be able to decrypt it straight up because they encrypted it with
books tell you that AES default mode encryption, that ECB encryption is insecure. They don't tell you why.
Read applied cryptography and then burn it, and then read practical cryptography, which is the follow-up book to it, which is actually awesome. Even practical cryptography, which is a great book. Practical cryptography says ECB mode is insecure for a bunch of reasons, including the fact that it leaks information about the plaintext. But it doesn't leak information about the plaintext.
You actually read news stories that say, oh, we took the time to search the key space from 2 to the sunexplode power to 2 to the sunexplode minus 1 power, right? And people actually think that stuff is actually important. We can straight up decrypt this, right? It's not insecure because there's some great mathematical attack you could do against it. This is simple arithmetic.
So how long does it take to do that? It takes 2 to the 16th. It takes like around 60,000 requests to the server. It takes nothing to do this against a server.
So it's 256 requests per byte. You need 255 requests to build the dictionary, and then 1 request to do the compare. And so for as many bytes as you want to decrypt, it's 256 requests times the number of bytes you want to decrypt.
So we said we're going to break this up into sections. That was round 2. Nobody had questions from round 1. No stickers. Anybody have questions here? I don't know if we're going to make it to the end of the talk. So, question. Say what?
Yes. We can do it Unicode too.
Can you repeat the question?
He'd like to know if the plain text was in Chinese or Korean, if it would work. And yes, we can decode Unicode too.
That's actually a really good question that's going to be relevant in the next round that we do. But here, this is not based on the frequency of characters. This is based on a fundamental property of the default mode of AES encryption or block cipher encryption, right? Doesn't matter what the data is. It could be compressed audio. You'd still be able to decrypt it, I think. Somebody's going to call me on that, and I'm probably wrong about it. Sorry, Colin.
So do you have everything you need to re-encrypt with admin equals 1?
You do, because the server is encrypted. I'll get better at repeating the questions. So
what he asked was if we have everything we need to know in order to be able to re-encrypt it and send it back to the server.
I'm so excited to answer that question that I couldn't repeat your question. So you do, because the server is encrypting things for us. It's acting as an oracle here, right? So there's something in common with all of the attacks that we're describing here today, which is that we're not using cryptography in the sense that Bruce Schneier talks about cryptography when he writes books about it, right? We're not using cryptography to keep nation states from reading our email, right? We're using crypto in a totally different setting, which is to enforce policy. And more importantly, we're using crypto in a setting where we have a server that wants to enforce policy, access control, what files we can download, how we protect our profile information and whether we're an admin. Enforce policy by holding a secret, exposing the ciphertext for that secret, and then letting the user interact with the application, assuming that the ciphertext is going to be perfectly safe because AES is unbroken, right? And this is a demonstration of why that doesn't really work. Right? It's because we're in a situation, the attack that we described here is called an adaptive chosen plain text attack. And crypto terminology is just anathema if you want to learn stuff and actually break things with it. But adaptive chosen plain text. It's chosen plain text because we control some of the bits of the message. In this case, we control a lot of the message, right? It's adaptive because we can make requests to the server, see the responses to the server, and then make new decisions based on what those responses were. So for instance, we can find the encryption of all A's and then recognize it because the bytes repeat. We're adapting based on the server's responses. And that's working because the server holds the key, does things for us that secretly reveal things about the plain text or how it's encrypting things, and allow us to make decisions about it.
The longest yes, so that Tom just went through that many words to say yes.
You're mean and a ruiner.
Yes, I am. I am a ruiner. But we need to get busy.
We don't need to. Any other questions? I'm killing time, man.
There's a length limit on requesting the server by requesting the block first.
Can you stand up and repeat that, please? Because I can't hear you.
Could you have the number of requests to the server by requesting the block first and then building the dictionary afterwards?
Requesting the block. So he's asking, could you have the number of requests to the server by doing something involving sending the block first and then building the dictionary?
No. You need to get a unique request for each piece of ciphertext you're putting into the dictionary.
Unless the answer to that question is yes, because we didn't care enough to optimize because this goes so fast, in which case, again, I'm sorry, Colin, it's probably possible to do that.
So I could have optimized for the set of printable characters and just done 20 to 7E, right? And that would have taken the number down somewhat. But at some point, you're going to get control N in there that you're going to miss.
There's actually a lot of different ways to write the attack. I wrote it differently from Mike and then yelled at him about the way he wrote it. And as long as you get the concept, you're fine. There was another question in the front row.
So if there's a character limit on any of those inputs, then that would potentially break. Like you wouldn't be able, you could only.
Also a good question. Your question was, if there's a character limit, a limit to the number of bytes that you can stuff into the message, could that potentially keep us from decrypting all the way to the end of the message? I don't think that's true. We had an argument about this, and I haven't thought about this hard enough, but I don't think that's true because the condition is not that we can get enough A's into the message to back the whole message into. Mike thought it was, but Mike's wrong. The condition is, do we know how many of the known plain text, how many of the bytes do we know? And can we get a condition where there's a block that has all the bytes that we know and then one more byte? If we can get 15, 16, 17, 18 bytes of known plain text that we learn byte by byte, which only requires us to be able to put in like 32 bytes, like a normal name or something like that, right? If we can get that condition, then we can repeat the attack, just cycling it through bytes that we know all the way through the message.
So you can do forward blocks instead of backward blocks. I implemented it with backward blocks because there was no length extension, or because there was no length restriction. You can do it with forward blocks, right? If I do this block and I get these 16 bytes, now I can just move a block forward and do the same thing with the next block. So as long as I can get at least 16 bytes into the message, I'm golden. I can move forward or backward. I did it the easy way because it made the animation look better. It's a good animation, right?
Okay. now I get to stand here and do my slides, right? Because they're my slides, and you can.
This is the part where I'm very quiet.
Yeah, that's going to happen. Okay. So we've seen encryption now with URLs, where they were signing the URLs to keep us from downloading arbitrary files. We've seen encryption now with session parameters. That, by the way, that whole thing with the session cookie and all that, and it's encrypted, and we're playing with the data and all that, it looks far-fetched, but it's really common. Every mainstream web framework does something like this. .NET does something like this. Rails does something like this. So we saw encryption in the session token. Now we're going to look at encryption in the place where it happens probably most frequently anywhere, which is, wow, that's bright, password resets. So if you look at the orange text in the bottom, you don't need to literally read that text string, but there's a password reset token, right? Password resets are probably the place where developers use crypto the most. Again, developers should never use crypto. It doesn't work for them, but here's where they use it the most. And there's a good reason for it here, right? Because with password resets and with email confirmations, we're in a situation where people like intrinsically have to get beyond the web security model and the web state model. There's no way to share state between an email message and the web and all that, right? So they use encryption to keep them from having to do lots and lots of database entries instead of long random key strings. They can just push the data out to the email message, then read it back from the email when it comes in. When you look at password resets that are big and long, chances are they're probably encrypted. So really common to see password encryption. So we were doing demo for, this slide is so annoying, but it's awesome. So we were doing the demo code for this, and I realized what a pain in the ass it is to test password resets. I realized that every time I've had to do this, I actually have to go in and actually go into my a special Gmail folder and copy, cut, and paste and all that stuff, all the little tokens in, and put them in a text file and play them through Burp or whatever, right? Giant pain in the ass. So what I did here was, what I wanted was a mail service that could live on a domain somewhere and accept arbitrary emails from anywhere, from any address at that domain, slurp out the URLs from them, and put them in a database. And instead of figuring out how to configure a mail server to do that, I just wrote a 150-line Ruby script that speaks enough SMTP to accept mail from things, and it just regexes URLs out of every mail that it receives and sticks it in Redis. And I apologize in advance for the non-crypto spiel I'm about to go in here.
Well, I just want to say that this is just another one of those examples why Event Machine and Redis are freaking awesome. right? Because just the ability to do stuff like this, and if you needed to do something like this on an engagement from scratch, you could sit and do this literally in 2 hours.
Event machine is Ruby's default event library. That's how you write evented code in Ruby. And because this is evented, this mail server is probably faster than SendMail, right? Also because SendMail is terrible.
Well, isn't everything faster than SendMail?
And then we're using Redis, and Redis, event machine and Redis are like, use Redis in your fuzzers, and every one of your fuzzers is going to be like 1,000 zillion times better. It's like it's almost like a database that was designed to build fuzzers in. And true fact, it was written by the guy who wrote HPing. Redis is amazing. Use Redis, even if you're not going to do crypto stuff, play with Redis, start using it in your test stuff. Redis is awesome. But long story short, we have a thing that made it easier for us. Like, you're not seeing a lot of our demo code right now, so I'm sorry about that. But we have a thing here that makes it easy for us to slurp all of the password resets when we're testing things, right? So we do 1,000 different password resets, and we get them all in a database, and we can do online analysis of them. So this slide is totally broken, and I'm sorry about that. So we're trying to get through the build that I ill-advisedly put here. But here's one of those password reset tokens, right? And yeah, this was an ill-advised build on my part, but it's fun to do this stuff with Keynote. So what we want to do here is kind of roughly the same thing that we were doing when we were doing default mode AES encryption, right? Which is we want to play with the email addresses that we're putting in here and see how they change the reset tokens that we're getting. So what we do is we grow the email addresses that we're sending 1 byte at a time. We don't have to have valid email addresses, kind of like we have our own mailinator to do this with, so it's really easy to do that. But we grow them 1 byte at a time. Now, if the tokens grew 8 bytes at a time, we'd know that they were probably using a 64-bit block cipher like Blowfish. If they grew 16 bytes at a time, we know they're probably using AES. Here, even though you're not seeing it, what we're seeing is that they're growing 1 byte at a time, which you can't even see, but trust me that they're growing 1 byte at a time, which means that we're looking at a stream cipher and not a block cipher. So what we want to look at here is vulnerabilities in stream ciphers and how to deal with stream ciphers. So the first thing I'm going to show you here is the oldest crypto vulnerability in the book for pen testers. Everyone knows this one, right? But I'm going to go over it anyways. This is classic stuff. This stuff broke VPN software in like 1995, right? But the basic idea here is you have a stream cipher, it generates a key stream. And then what we do is we combine the key stream with our data with the XOR operation, and that's how we mix the data together. And the vulnerability is if you ever encrypt the same data with the same key stream. So for instance, if you use RC4 and you repeat the same key for multiple encryptions, what you get is multiple messages encrypted with the same key stream. And that's devastating. What that gives us is messages that we can XOR together to cancel out the key stream. So 2 ciphertexts encrypted with the same key stream XORed together give us the plain texts XORed together. Now there's a bunch of different ways that you can attack plain text XOR plain text when you have a repeated key stream. Chris Eng gave a talk here. I've angered Chris Eng, and I'm very sorry, Chris. But Chris Eng gave a talk here a while ago. It was an awesome talk where he showed how to kind of back out. Like, if you know some of the plain text in the message, you can XOR that plain text into the message. And if you XOR known plain text into the plain text there, you get the original message, and you can go back and forth between the messages and work it out, right? I'm going to show you a different way to do it. It's obnoxious, but it does not require you to know anything about any plain text in the message, right? So the property that we're going to exploit here is this. So when you read papers or read people writing up how to attack, say, RC4 when a key stream is repeated, they talk about what happens when you XOR 2 messages together. But we're dealing with web apps or applications in general here, and it's not a whole lot harder for us to get 10, 50, 100 messages all under the same key stream as it is to get 1 message or 2 messages under the same key stream, right? It's an application that's doing it for us. So what we're going to do is we're going to grab a bunch of messages. Right? We're going to grab 101 messages. And we're going to designate one of those messages, the first message. We're going to designate that as our kind of key message, our Rosetta Stone message, our magic message. The rest of them, we're going to cat together. So say we have 50 byte messages, and we have 100 of them, and we cat them all together. That's like 5,000 bytes, right? I can do math. And so what we effectively have when we do that is 5,000 bytes in 50 byte chunks. I think that's true, but I can't do math. And then each one of those messages is effectively can be XORed against that original first message. What we have here is effectively the analog of XOR encryption with a repeating XOR key. So that's a high school or freshman in college crypto exercise. People that take crypto classes, their professors will show them how to do this. But it turns out to be really, really straightforward to break. Now, this is probably one of we talked about how to break AES here. We talked about how to attack SHA-1. This is the most obnoxious piece of crypto exploit code you're going to have to write, and it's to break freshman in college crypto. Mike got very, very upset when I tried to walk him through this.
It made me cry.
It literally, like, he thought I was messing with him. He thought I was fucking with him, and it wasn't real.
This is not possible. You can't do this.
So I'm going to kind of really quickly go through how you break repeating key XOR encryption. This is encryption when all we're doing is taking the string key and XORing into the message over and over again. So first 3 bytes against key, next 3 bytes against key, next 3 bytes against key. So normally when we're doing that, when we're trying to break that, what we do is we try to discern the length of the key. And so what we do is there's a statistical test that we can run based on collisions in the message to see if it's a 2-byte key. We'll be able to run a statistical test to see if it's a 2-byte key. If it's a 3-byte key, that same statistical test will tell if it's a 3-byte key, or if it's a 4-byte key, or if it's a 5-byte key. We're going to keep doing this until we find the length of the key of the message. We don't have to do this in this case because we know the length of the key of the message. It's 50 bytes because it's that first ciphertext that we designated. But if we were doing this in actual repeated key XOR, this is what we would do here, right? Is we'd find the length of the key. Now that we know the length of the key, what we're going to do is we're going to bucket every character of the ciphertext here, every character of the message. We're going to bucket into, a bucket of the first bytes, or every second byte, or every third byte of the message, or every fourth byte of the message, or whatever. We're going to wind up with, this is a 6-byte key. We're going to wind up with 6 buckets, so 6 strings of messages, all encrypted under the same single byte. So now there's a question earlier about, did the attack that we did earlier work if the message was actually Korean or Chinese or whatever, right? Well, here's a case where that does matter, right? So the most common character in normal English text is space, followed by E. But long story short, if you know the most common characters for a message, what you can do is, all you do is, you go from 0 to 255, every possible byte, and you XOR that byte across the whole message. And whichever byte produces the most spaces, or the most E's, whatever the most common Chinese character is, that's the key for that row. You do that over and over again. If this animation was awesome, it would show you the key on the side, but whatever. But for each row, you do that test again. Which byte gives me the most spaces? Or if it's comma-separated values, which byte gives me the most commas? I have to make guesses there about what the most common character is, but that's the only thing I need to know. I have to test for the most common character in my plain text. And when I find it, I'm going to get the byte for that row. That's how you solve repeating key XOR. But that also breaks the plain text or that ciphertext XOR ciphertext thing that we did before. So we have before is 100 messages concatenated together, effectively all XORed against that first message. And this exact same test solves for that as well. We did like a crypto challenge. The time that I made Mike cry and other people mad at me. We posted some messages to Twitter and said, can somebody decrypt this? And I actually wrote a script that solves for repeating XOR. It's a really short Ruby script, not because I'm smart, but because this is really easy to do. And so I was talking to Mike about this, and we literally just did this, right? We did, I think we used RC4, but whatever, right? We encrypted a bunch of stuff with RC4, and we catted them together, and we just fed them to the script that we used for the kindergarten crypto, for the 3-byte key or the 5-byte key. And it solves for the original content of that first designated ciphertext message. So we had 101 messages, we designated one of them to be the key, and we can solve for it. And we get the 50 plain text bytes for that key, for that message. When we have that, we can XOR that against every other message and get the messages for that. We instantly get all the rest of the messages. We've encrypted it completely when we do that. So that's, I don't know how to pronounce that word, but this is the last argument in the world I want to see is between you guys right now. So anyway, there's a name for it. I don't care what the name is, but your script that you write to break repeating key XOR will also break RC4, and it'll also break AES in best practices mode. So what you're seeing on the screen here is the short amount of Ruby code required to take a Ruby AES library and implement counter mode for it. Counter mode is the way that you take AES and you turn it into a cipher that works like RC4, a cipher that encrypts a byte at a time instead of 16 bytes at a time. Counter mode is a lot more convenient to encrypt with than CBC mode is, where you have to pad the data and all that. Counter mode is also the mode that Bruce Schneier recommends that you also do. And what you basically do is, in counter mode, instead of encrypting the data, you encrypt a counter and a nonce. A nonce is a number that never repeats, and it's a number used once, right? So you encrypt a 64-bit nonce with a 64-bit counter that increases every time, right? That's counter mode. And what that does is each time you encrypt that, you get like a wildly different 16-byte block. And those 16-byte blocks are your key string. Right? This is the way that, if ECB mode is the default mode, this is best practices mode encryption for AES or whatever ciphers that you're using.
So basically, simply, and the way I like to think of it is, you have a bucket, and that bucket has random bytes in it that you set up with a 64-bit number, and you pass the plain text that you want to do. And every time a byte goes over the bucket, it goes in the bucket, gets it stored with the thing that's in the bucket, and comes out, and now that's encrypted. And then the next byte does the same thing with a different byte, again and again and again, and that's how a stream cipher works.
And you can't see it because I ill-advisedly dimmed it out at the bottom. But like I said, there's a nonce and there's a counter. And you increment the counter as you go. But the nonce has to be unique for every message that you, like every time you're going to encrypt something new, that nonce has to be different. If the nonce ever repeats itself, you get the same key stream all over again, just like an RC4. So when people encrypt with RC4, they have to be careful not to repeat keys, message by message. They have to have a different message every time, right? A lot of people use RC4 encryption because it's short and easy to write. You'll find a lot of web apps out there using RC4. And you can test very straightforwardly whether they're using repeated key streams. Just do that stupid repeating XOR attack, and if it works and gives you something legible out, they repeated the key stream, right? But with AES and CTR mode, and best practices AES mode, right, there's more you have to look out for than just, did I reuse a key? So the first thing that can happen is that the nonce could be 0 or just not initialized properly. The nonce could repeat for every message. Very, very smart people have made this mistake before. There is very, very good crypto software out there where the developers, whose only goal in life was to build crypto software that did not have vulnerabilities that could be broken by high school students, have written software where the nonce wasn't initialized properly. And so they ended up accidentally encrypting whole swaths of messages all under the same key stream and allowing it to be broken XOR style, right? So you have to watch out that you actually initialize the nonce properly. You have to watch out that the counter doesn't wrap. If you look at encryption in embedded systems, which is something we do a fair bit of, you'll get environments where people will use restricted counter spaces, because the standards aren't super completely totally clear about how the nonce and the counter are actually encoded in that block. So people will say, well, I'll make more of the block the nonce and I'll make less of the block the counter, and they'll do a 32-bit counter instead of a 60 or a 64-bit counter, right? Well, that 32-bit counter is easy to wrap. It's only 4 billion bytes. And when that counter wraps, you have the same problem again. You're repeating key stream again. When you read books on encryption with AES and counter mode, with AES and the best practices mode, right? One of the things that people tell you that AES CTR is good for is random access to data. It might be good for bulk encryption or disk encryption, because you can seek forward in the message. You can jump like 1,000 bytes in. You can't do that with AES in CBC mode, which is like the most conservative mode, right? To decrypt 1,000 bytes into a message or 10 megs into a message in CBC mode, you have to decrypt every block that led up to it, because all the blocks are related. In CTR mode, you can generate the right key stream block for anywhere in that message just by incrementing the counter and generating the key stream, right? But if you have an application that allows you to seek forward like that, read the data, see what it was, and then change it and put it back in there, you can have a situation where people will re-encrypt the data with the same counter. Again, they're creating a situation where the key stream accidentally repeats itself, and that block of the data is going to be decryptable. So I said that people will accidentally make the mistake where the nonce can be 0. People can stumble into bad ways of generating nonces. We've done embedded systems where people have thought it was a good idea to have the time be the nonce, because the time's never going to repeat. It's monotonically increasing. It's always going to go forward. It's obviously not true, right? So you'll see messages where the header for the message has like a timestamp field, like a 32-bit seconds granular timestamp field in it. And they'll use that as the nonce, because it's an easy way to generate a number that isn't going to be repeated, except if the server ever sends more than one message in a second, which is really easy to do. Every time the server sends more than one message, 3 messages, 10 messages in the span of a second, they're all under the same key stream. They can be broken the same way. In like 1996, we had like the buffer overflow renaissance. I bring this up in every talk, and I'm sorry for doing this, like being a broken record on this. But like 1996, we had like the buffer overflow renaissance. We had this problem where people are using the C function stir copy to copy strings, and stir copy isn't bounce checked. So you can run off the end of a buffer, and that's a buffer overflow situation. And so the fix for that is really straightforward, right? You just change stir copy to stir end copy, which counts properly, and everyone's happy. Everything's counted now, we're checking bounds, that's the solution, right? And then like a year or 2 years later, somebody realizes that if you subtract 1 from 0, you get a really, really large number, and you pass that to stir end copy, and now it's unbounded stir copy, and now we have the whole integer overflow renaissance. It's not enough to know that the nonce isn't supposed to repeat. You have to write your code so that it's impossible to coerce the nonce into repeating. You have to write the code defensively, so the counter can't possibly repeat, so the nonce can't possibly repeat. Whatever you do has to be resilient to attackers who are going to try to find ways to get around this. Now, very competent, very popular crypto software has been written where the nonces were zeros. That's the state of the art that we're in right now. It is not true that software right now is written to be resilient to attackers trying to coerce situations where the nonce repeats. And when that happens, you get exactly the situation we just talked about, where you're able to break messages that are encrypted in the best practices mode for AES using high school cryptography.
Yep. But if you think about the way we pen test this stuff, right? We always when we're doing black box stuff, and we're always black boxing against cryptographic systems like this, right? We're always doing stimulus response testing, right? That's what we mean when we say coercing the server into doing something stupid with its nonce, right? If you can use messages to the server or any kind of stimulus you can send to the server to get the server to do something stupid with the nonce, you win. That's the win.
So here is a point in the talk. There was a whole bunch of questions, and I totally forgot. If anybody wants a sticker, come up and I'm exploitable. You can get a sticker from me. But questions for this? This makes total sense. Questions are your way of proving you paid attention, as somebody who then died terribly said to me once.
Yes?
If you had a better timestamp, like the millisecond, would this solve the problem?
Of a time-based nonce?
Wait. You have to repeat the question. If you add a millisecond timestamp...
I'm sorry, I'm a total nerd. Right?
If you add a millisecond... So your question is, if you add a millisecond timestamp instead of a second granular timestamp, would that improve the security of the nonce?
Mike jumped in because he thought I was going to throw my water at that person. So, no, yeah, it's a great question, right? Like, would simply increasing the granularity of a timestamp do it? Timestamps are not nonces, right? Like, secure software is going to generate... The reality is when you're working with nonces in counter mode, right? The nonce is effectively like the key. In fact, its function is to feed into the key stream and make the key stream secure. Secure software treats that nonce as if it was a 64-bit sub-key of the original message. And when you look at code that carefully generates nonces, it'll tend to generate the nonce the same way it generates the key. By the way, everyone in this room should know that when you generate crypto keys are always random strings. They come from your secure random number generator. They aren't strings.
So let me just give you a real world example, right? Think about a high frequency trading firm that's actually running in femtosecond latencies, right? If they're sending trades to a server,
femtoseconds?
Right? Yeah. If they're sending trades to a server that fast, then a millisecond granular timestamp does not help you. Right?
So it's a great question, but the reality is that when you generate a nonce, it should be a cryptographically secure random number. It's the right way to do it. And if you don't generate a cryptographically secure number, you're in a situation where instead of being as secure as AES, you're now as secure as the mechanism that you use to generate the random number is. So, and that's the answer to that question, but thank you for asking that question. Any other questions before we proceed? No. Okay.
I just want to say femtoseconds because I really like that word.
So we have like 15 minutes left in this talk. So we could do Frisbee-Hellman. Or we could explain Frisbee-Hellman and go on, and then people can see SRP. Because if we do Frisbee-Hellman, we're not going to do SRP.
Who here can throw a Frisbee?
No, yeah, it's not going to work. So I vote that we're not going to do Frisbee-Hellman. You're just going to see us talk about what we're going to do with Frisbee-Hellman, learn what we came to learn here about Frisbee-Hellman, and then we'll proceed as if we had thrown Frisbees in the audience. They're beautiful Frisbees, but I think...
Show one, Timmer. Stand up with a Frisbee and show them what
But you need to see the SRP attack, and we need to get through this. So here you go. So imagine, if you will, I had asked you guys to open up a Ruby window with an IRB in it, a Ruby IRB window, and then punch these things in. So P is 29, which is a small prime number. And G is 2, which is a number that we're going to use to generate numbers within the ring of all those numbers from 0 to 29, right? And then A is a small random number. A is rand P. It's a number between 0 and 29. And then so that A, that lowercase a, this is, by the way, a form of encryption that's very different from any of the encryption that we've talked about so far. This is number theoretic encryption now. Just we're going in a different direction here, right? So that lowercase a is our private key. Now, obviously, you can look at this and know 29 and 2, not cryptographically secure long prime numbers. You would go to NIST and get one of those giant long hex strings that's a secure prime number. But here we're using small numbers because ostensibly we were throwing Frisbees with them on it. And then you generate a public key, which is simply G raised to the power of a modulo P. So it would be 2 to the 29th power mod P. Mod P just means it wraps around every time it hits P, right? And what you've done there is you've generated a public and private key pair. And so what we're going to do here is, theoretically, I threw you a Frisbee. And that Frisbee had a number on it, uppercase B, which is my public key. You have your lowercase a, which is your private key. You have your uppercase a, which is your public key. And what you're going to do is, you're going to take my public key and your private key, and you're going to combine them. And all you're going to do, using high school math here, is you're going to take my uppercase B, my public key, and raise it to the 8th power. That's a line of Ruby code. It's that simple to do. Raise it to the 8th power modulo P. And you're going to come up with a number. And we're going to call that number your key. So I sent you that uppercase B on a Frisbee. Anybody could have seen it.
Yeah, it could be flying through the air with the number spinning around. It'd be kind of
Everybody sees uppercase B.
Yeah.
Everybody sees uppercase A. Everybody sees the public keys. Nobody sees the private keys, right? And by doing this, we both come up with a number that only we know. Even though everyone saw the uppercase A and the uppercase B, nobody knows what the lowercase a or the lowercase b are, and nobody can get key right there without knowing either the public or without knowing one of the two private keys. Obviously, again, doesn't work with P is 29, but it does work with P is a 124-bit random number, a random prime number, right? So that's the Diffie-Hellman protocol. So assume instead I had done that, You did the same thing where I threw a Frisbee, and you combined the numbers. You took your public and private key pair that you generated with one line of Ruby code, and you raised the number that I sent you to your private key's power to do a Diffie-Hellman exchange, right? But assume that instead of, in good faith, sending you a randomly chosen number between 0 and 28, a valid number that was mod p, assume that I instead sent you 58. And you did the math. So you would raise your public key, you would raise my public key b to your private key's power. You would raise 58 to the 8th power modulo p. Anybody here know what you get if I do that? Did somebody say something? Say it louder. You get 0 when you do that, because 58 is 0 modulo 29. It is, isn't it? I think it is. I can't do math at all.
Yes.
It is. It's 0 modulo p. And you know from grade school math, I think my daughter knows this, that if you multiply a number by 0, you get 0. It effectively cancels out that calculation right there. Okay. That was a very again with my terribly.
I thought we were getting attacked by clowns. I was like, where are the no clowns?
That's mean. So this is kind of an interesting toy. Well, so we described the Diffie-Hellman protocol here, where I send a number, you send a number, we raise them to each other's power modulo p, right? And here's a toy vulnerability with Diffie-Hellman. You'll see people write up posts about, like, smart people have found IPsec implementations where the IPsec protocol would take p or p times p or p plus p as a public key value, feed it in and generate 0 as the private key.
And this was literally going to be a toy vulnerability because we were going to do it pen and paper on Frisbees with a man in the middle.
It's not really that big of a deal, right? Because in Diffie-Hellman's already man in the middle-able, right? The man in the middle just runs the whole Diffie-Hellman protocol with each side of the protocol, and then is able to get, like, Diffie-Hellman's already not secure unless you have something else to make it secure. Diffie-Hellman, very, very important protocol. It's good to know this about Diffie-Hellman, right? Because Diffie-Hellman is a fundamental building block of a lot of important crypto, right? Like, ephemeral perfect forward secrecy mode in TLS is based on Diffie-Hellman, right? So knowing this and knowing how you could zero out, a Diffie-Hellman exchange is good to know, right? But it's not like fundamental. You're not going to break a lot of apps with it. But here is a way that you're going to break a lot of apps by knowing how that Diffie-Hellman things works. So I want to talk really quickly about the secure remote password protocol, or the Stanford remote password protocol, or whatever. So SRP is probably the best known way of cryptographically doing challenge response password authentication. There's like an initiative to bake SRP into the TLS protocol. A lot of smart people have built applications that use SRP as their secure login system. There are web apps out there that use JavaScript crypto, don't get me started on JavaScript crypto, to do the SRP protocol so you could do secure password exchanges without having all of TLS there or whatever, right? With all of SSL there. So the SRP protocol is a way of cryptographically proving that you know a password. And there's the math for it on the board. Now, the math here is not hard. When you look at the SRP math, all you're seeing is numbers multiplied and raised to powers.
That math looks hard to me, I don't know.
It's really not, right? Like, the notation's a little bit terse. But this is what you get on Wikipedia when you look up SRP. But I could explain what all these things are.
No, but C is client, S is server. That's all you need to know.
Okay, that's actually good to know, right? That's C to S is the client to the server, S to C is what the server sends back, right? So instead of explaining all these different things to you with SRP, just proving that we've actually looked up SRP and know how SRP works, here's a simplified model of what SRP is, right? The client sends to the server capital A, their public key, a large number modulo a large prime number, right? And then the server sends back to the client capital B, which is its public key. Now, this should look familiar to you. This should look very familiar to you because I just hypothetically threw Frisbees at you about it. It's fundamentally just Diffie-Hellman. Except instead of normal Diffie-Hellman, all we're doing is we're mixing the password into the server's public key in such a way that the Diffie-Hellman math is only going to work out if you happen to know the password. The client can only come up with the same shared key as the server if the client knows the password, because the math is based on, and the way you combine the password is you just hash the password, and you treat the resulting bits as an actual number, and you mix that into the calculation, right? And it's more complicated than this. SRP has a lot more functionality to it. It's a little bit trickier than this, but not in any way that matters to you when you attack it. So if you guys were paying attention with the vulnerability that we just talked about with DH, I'm hoping that it's somewhat obvious to you what the problem is with SRP, which is that the client generates a public key and sends it to the server, and the server is going to send a public key back, and they're going to prove to each other that they arrived at the same key, which should only be possible if the client knows the password so we can make the math come out the right way. Well, the client has another way of making the math come out the right way, which is that the client can send 0 as the client's public key and zero out the computation the same way that you can do a man-in-the-middle style thing with Diffie-Hellman. This is also really well known. There's a section in the bottom of the SRP specification for don't do this, don't accept values from the client that have 0 or 0 mod p. And you'll find a lot of code that checks. Like a lot of people that have implemented SRP will check to make sure the A value that came in from the client isn't 0. But that same code doesn't check to make sure that the A value isn't P or P plus P or P times P or some other large number. Think about it for a second and you see there's an infinite number of possible things the client could send to the server that would zero out the key. It's every possible multiple of P, the number that we're sending there. So you have to check that it's 0 mod P and not just 0. This is an awesome, awesome vulnerability. I would say more than half of the people that have ever implemented SRP themselves, more than half of the very competent people who have implemented SRP have not written this check or wrote this check improperly. When you see SRP in a pen test, if you don't find this vulnerability in it and this vulnerability is present, you weren't competent to do that pen test. You missed the most important vulnerability in that application, which is that people can log in without a password. This exploit's also really easy. If you have a library that the client is using to do SRP auth with the server to log in properly, right? All you do is you take that client library and where they have like the variable will probably be called uppercase A, right? Change that variable to be 0 instead of uppercase A and then run the library. You now have a client for that SRP implementation that allows you to log into those servers without passwords. You will find this on Pentest. You'll find this all over the place. This is probably the coolest, it's the most payoff for any crypto vulnerability that we have. So
do 36 chambers.
Because we have 15 minutes left.
We have 10 minutes left.
We have 10, oh, we have 10. Wow, okay. We timed this well. Well, you guys are missing the RSA equals 3 math explosion, but if you
just show the slide, because it's a good.
He just wants, because he put Soda Popinski on his slide that you guys can see. So yes, we have Soda Popinski. There you go. And while Soda Popinski is on the screen. So first of all, questions about Diffie-Hellman, which I blew through because we're running low on time, and SRP. I'd much rather, if you guys have questions about SRP, you ask me this now instead of 36 chambers.
So this is where I actually got to talk again, so I'm sad that I don't get to talk again.
I'm not. So any questions about SRP? Any questions about Diffie-Hellman? No questions about Diffie-Hellman or SRP. So I guess the last thing we want to talk about here, we're not really going to talk about it much, but it's something we're going to give to you guys. So over the past couple of years, we've had a tool internally at Modisano called 36 Chambers, which is kind of like WebGoat, but for crypto. If you guys are familiar with WebGoat, it's a web application that has every vulnerability known to man in it.
Except this one. We got to put this one in there.
36 Chambers is a series of challenges that demonstrate each one of these vulnerabilities and a bunch more vulnerabilities. CBC Mac is in there. We didn't talk about padding oracles because padding oracles have been talked to death already. You can go read Ty's paper or that blog post that we wrote a long time ago about padding oracles. But padding oracles are in 36 Chambers, right? We'll post, watch us on Twitter. Watch Modisano on Twitter, and we'll post the URL, or you'll find the URL. But we're going to do, I guess, open access to the tool that we've been using to train our testers. And there's like 15, 16 different, and each one of the tests is, unlike WebGoat, which kind of walks you through everything and tells you what you're testing, the whole point here is figuring out how to attack things where you don't have the source code for them, where you're in a black box position testing the app. And that's how 36 Chambers works too, is the first thing you have to do on each one of these things is find out what the encryption constructions were used to actually enforce the security for it.
Again, the point is to teach people, is to help people who normally just look at web applications, see great big blobs of binary crap and say, oh, I'm moving on to the next thing, right? It's really easy with a little bit of experience to figure out what each of these things actually look like, and then once you figure out what they look like, how to attack them in very simple, step-by-step manner.
Pen testers are not good enough at testing crypto. I use, for a long time, I thought of myself, what I do, I break software professionally, that's what I do, right? And I thought of myself as, I do practical security, which is the kind of security that you do when you're not doing crypto. That crypto stuff, that's like advanced academic, security stuff. That's not practical security stuff, that's like theoretical security stuff, right? Which is total bullshit. Yeah, when things are encrypted, they're probably broken. There's so many more things that if we had more time to talk about, we didn't get into lattice theory because I don't know how lattices work, but
he can't do long division. He can't do long division.
I can't do long division either, but there's so much that goes wrong with crypto. No matter how much experience you have testing applications, take some time, go through our challenges or somebody else's challenges, and actually go through figuring out if something has length extension, figure out if something has HMAC timing vulnerability, something like that, and actually run the exploit. It's the only way you're actually going to know how to do it, and stop missing things like this or that that big sort of Babinski I keep pointing to on pen tests. So,
So first of all, they're awesome. Like when you actually find them, the person that you find them for goes, ooh, and then you get rehired and you get more business. That's what we like.
so we'll post a link. We'll give invite codes to people. You guys can log in. There's a scoreboard. We keep track of how people are doing. We add challenges to it all the time. We're trying to keep a pretty good catalog of all the crypto vulnerabilities that you can practically exploit. And any crypto construction you use, message authentication codes, public key crypto is terribly riven with vulnerabilities. Stream ciphers, block ciphers, hash functions, whatever. Any one of those things, we can tell you and give you examples and give you a playground to play with, vulnerabilities that happen in those things. And they're really hard to get right. You have to get all of those things perfectly right to make a crypto system work. And so we're giving people a demonstration of how to do that. Anyways, I think we landed exactly on time. Any final questions? Happy to field them. And thank you guys. Thanks for letting us talk about
5
this.
minutes left?
Well, see, I ran through it all. Now everyone has to sit in silence for 5
Are there
minutes.
any other questions? Because we would love to answer them.
We had a whole other vulnerability we're going to talk about here if anybody wants to see how RSA attacks work, or a really simple RSA attack.
Very simple RSA attack.
You can bug Mike about it. I'll watch and laugh. So. Practical cryptography. Everybody has that red book on their desk, which is applied cryptography. Burn it.
Yeah, one of